In this lesson, I'd like to show you how you can create your own algebraic equations. So if you're wondering where all that algebraic thinking comes from and all those equations that we've been solving, I'm going to try to give you kind of a sneak peek at how we could create our own. So this is a 7th grade math lesson. It's called Creating Algebraic Equations, and your learning target is to create your own algebraic equation using rules of inverse operations. And I'm going to try to show you how now. So I want you to have some extra space out. If that means that you're on your notes packet and you have some extra room, an extra blank page, that's awesome. If it means you want to get out some lined paper, that's fine as well. So again, we are going to create an algebraic equation. I know this is going to be earth-shattering. I'm going to show you the first equation, x equals 1. You might say, well, that's ridiculous. I don't have anything to solve. And you'd be absolutely right. So I want you to think about this. We have learned the rules of inverse operations. So what I do to one side, I do to the other. Let's try that. What if I took away 2 from both sides? I'm keeping balance in the kingdom. I'm keeping balance in my equation. So I could write each side a little differently here. I could show you this as x take away 2 equals, well, what is 1 take away 2? A -1. This is a little more interesting, isn't it? All right, let's try it again. So what can we do next? I tried subtracting. Maybe I could try adding something to both sides. What if I added some x's to both sides? What if I added 3 x's to the left? Then I'd need to add 3 x's to the right. I don't know about you. I probably wouldn't put those variable terms underneath the constant for some weird reason I did that, but we'll make it work, won't we? So what's 3x's plus 1x? 4x. And I still have to take away 2, and on the other side equals, well, how about a -1 plus 3x? That's one way of writing it. This is definitely more interesting. I don't think many people are going to come up and just guess, hey, x equals 1. But in fact, looks like it should. Okay, that was fun. We tried subtracting something from both sides. We tried adding something to both sides. What if I tried multiplying something on both sides? What if we wanted to come up with, say, like a decimal answer or a decimal problem? What if I took everything inside times 0 and 1/10? I'm kind of showing you this in a distribution, if you will. So it means I'm going to take 0 and 1/10 times all of these terms. Well, what's 0 and 1/10 times 4x? You would get 0 and 4/10 x. What is 0 1/10 times 2? I would get 0 and 2/10. Notice it's a constant, so there's no variable with it. There was subtraction, there's still subtraction, and now I need my drawbridge, or my equal sign. On the other side, what's 0 and 1/10 times a -1? Well, that'd be a -0 and 1/10. And what about this 0 and 1/10 times the 3x? Remember, what I do to one side, I must do to the other, so I'm really showing you all the way through that I could apply this 0 and 1/10 times every single term. Well, I'm going to get 0 and 3/10 x. There was addition, there's still addition between these terms. Now this would be awesome. I would say, hey, this is an interesting enough equation that you could give this to your friend and see if they could solve it. And the truth is, they should be able to. So let's go ahead and do a quick check and see if it works out. So 0 and 4/10 x, take away 0 and 2/10 equals a -0 and 1/10 plus 0 and 3/10 x. Well, we've made this interesting enough. I don't think they're going to guess that x equals 1, unless maybe they see your paper. So let's see what we would do first. Maybe change a minus to a plus, change the sign of next. Maybe someone out there would say, I don't like those decimals. They're freaking me right out. Maybe they'd say, let's get rid of them. How many decimal jumps would I have to make on all of these numbers? Can't we really multiply every single thing in here times 10 and turn them into some nice whole numbers, or at least some integers? Well, 10 times 4/10 x would get me 4 x's. And 10 times a -2/10 would just get me a oops, come on pen, you can do it. Would just get me a -2. And there was addition, there's still addition. On the other side, I'm kind of using this distribution idea, but I'm making sure I grab every single term along the way, trying to get rid of the decimal. You don't have to do it this way, but this is one way to do it. Well, what is 10 times a -1/10? Well, it's just a -1. That decimal's going to jump or move one place to the right. And what's 10 times this 3/10 x? Well, it'll just be 3 x's. There was addition, there's still addition happening here. Oh, this looks better. My decimals are gone. That was fun. All right, well, let's try something else. We need to start gathering like terms. So I don't have anything more that I can simplify on the left, nothing more to simplify on the right. So we're moving to inverse ops, my friends. Let's get rid of this -2. Let's use the opposite. Let's use a +2 or add 2. Let's do the same thing to the other side and see what happens. Looks like we're going to get 4x equals +1 plus 3x. We're really close, aren't we? We have our constants moved to the right, so it probably means that we should move our variable terms to the left. Again, we're crossing the drawbridge. Whenever we go across the equal sign, we must use inverse operations. So over here on this side, 4x's take away 3x's leaves me with 1x. And on the other side, I'll just be left with 1. Notice, it checks out. We developed our own equation, which has a result or an answer of x equals 1. Awesome. Another way to maybe check this, I didn't think about that in a moment. Instead of solving it with inverse ops, we probably could have done some substitution. We probably could have put the 1s right in there for the x's and check to see if it would check out, and it would. Okay? I'm going to ask you to try another one with me, so let's get wild and crazy. What if x equals -5? Well, that's a pretty dull equation. In fact, nobody needs to solve anything. It's already solved for you. So let's make it a little more interesting. What if I decided to take, say, this side times 2/3? If I do that to the left, I better do that to the right. I'm using my rules of inverse operations. You might want to remind yourself, well, this is kind of like saying x over 1, isn't it? Okay, so I might get 2/3 x. And on the other side, I would have, maybe I'll write this as -5 over 1. This would be the same as -10/3. Well, this is a little more interesting already. I'm not sure if anyone would guess how I started this equation. Well, let's take it a little bit farther. Well, I decided to multiply something on both sides. What if I decided to add something to both sides? What if I decided to add 4 x's to both sides? What I do to one side, I must do to the other. So let's see what happens here. Notice this is not really inverse work. I'm showing the same, oh, it is inverse work. I'm not undoing things is what I mean to say. Meaning I'm going to add to both sides. I'm not trying to move anything, I'm just trying to make it a more complex equation. Well, I'm going to get 4 x's plus 2/3 x equals 4x plus a -10/3. This is definitely more interesting. All right, well, on the left side, if you're going to challenge your friend, you're going to want to combine these like terms. You're going to want to make it look a little more interesting. So maybe I'd call this 4x over 1. I could probably rewrite this. Would that be 12/3 x plus 2/3 x? Would really get me 14/3 x. Ooh, I like this. 14/3 x equals 4x plus a -10/3. This would be a challenging enough equation. I think this would be great for someone to have to think about a little bit. So what if I were to plug in that original answer? What if they were to solve with inverse ops and you just want to see if it's going to check out? Does it really end up working? Well, let's try it over here. I'm going to try it a different way. I'm going to try it without inverse ops, try some substitution. 14/3 times a -5, because that's what we originally said x was going to equal. And on the other side, I have 4 times a -5, because that's what we said x was going to equal, plus a -10/3. Oops, lost my negative, sorry. Let's see what happens if I simplify here a little bit. Well, I might write this as -5 over 1 for this problem. And I know 5 times 14 is 50 plus 20 more. Looks like I'm going to get 70. It's going to be -70/3. And on the other side, I want to see if it's going to check out. Well, 4 times -5 is a -20 plus a -10/3. Oh, this is -20 over 1. I can't quite combine that yet, but I could do a rewrite step. Maybe off to the side, I'd say, well, -20 over 1 is the same as -60/3. I want to add a -10/3. Oh, okay, on this side I'm going to get -70/3. So another way to check that this worked out, and again, your friend would have to solve this equation using inverse steps because they wouldn't know what the x was valued at. it checks out. The two sides end up being equivalent. So this would be an awesome equation to share with a friend. I'm going to let you try one more equation with me. We're creating our own algebraic equations. So what if we wanted x to equal 0? This might be a little bit harder to work with. So again, if you gave this to your friend, they'd be like, by the way, x equals 0. There's no thinking involved. So we want to step it up a little bit. We want to make it a little more complex. So let's think, what can we do? Maybe I could divide both sides. What if I divided x by 7? That sounds nice. If I do it to the left, I must do it to the right. Looks like I'm going to get x over 7 equals 0. That's a little more interesting already, isn't it? But that doesn't look challenging enough for my friend. So what could I do instead? What if I decided to add something to both of them? What if I decided to add like 1/8? 1/8 sounds fun. I could add 1/8 to the left, so then I have to add 1/8 to the right. Oh, so what would I get? Well, this side wouldn't change a whole lot. 1/8 plus x divided by 7, or x over 7, equals 1/8 on the other side. I can simplify this to make it a little more interesting for my friend. I don't mind it, but I bet we could do a little bit better. So what if we, well, let's see, we added something to both sides. We've divided. What if we multiplied everything? What could we multiply the entire equation by? Come up with something interesting. I don't know. How about 5? Yeah, make it a negative. -5 sounds fun. So -5 times 1/8 would get me -5/8. And -5 times x over 7 would be really like -5 times on 1x gets me a -5x over 7. And on the other side, can't forget to multiply. This is a distribution to the entire equation, all sides of the drawbridge. I'm going to get a -5/8. I noticed something. This -5/8 and this -5/8 sitting here, it might be too obvious for my friend. So the last thing I'm thinking is, what if we, could we do here to make that more interesting? I'm not sure at this very moment. I don't know. I'm trying to make it more interesting for you and another way for them to see it without these looking identical, these terms on either side. But maybe you would stop here and say, here friend, see if you can solve it. And the hope would be that if you really followed your inverse steps, if you did the same rule to the left and the right side of your equation, your friend is going to come back and say, well, x has to equal 0. X will be 0 in this situation. You yourself, before you give this to a friend, could check using substitution and see if it checks out. It will. Or you yourself could also use inverse operations, isolate the variable, and see if it checks out. All right, your challenge, your job right now, you get to decide what x equals. Oops, easy for me to say. And don't tell your friend. In fact, maybe this would be a good activity for table partners. Maybe 2 of you work on this together to make sure you're in agreement. And then in a minute, you can pass this to another friend. So start with x equals something we haven't tried yet. And then use your rules of inverse operations. If you decide to add to the left, you must add to the right. If you decide to subtract from the left, you must subtract from the right. If you want to try rules of division, do it to both sides. If you want to try rules of multiplication, do it to both sides. If you want to deal with fractions or decimals, okay. Why don't you try just applying maybe 2 to 3 inverse steps, and then give your equation, without the answer on it, give your equation to another table. So to another tag team, another duo, okay? And see if the duo can solve it using their inverse operations. See if they can figure out what your x was equal to. I wouldn't start with anything too crazy. I don't know if I'd make this negative 94.732, because that's a little bit nasty. But maybe something like a nice integer. See if they can get back to a nice integer. If it goes well, maybe you want to step it up next time, and maybe you want to get a decimal answer. Maybe you want to get a fractional answer. I want you to spend a few minutes trying this. I think it might be best to work in duos right now, so maybe table partner, and then in a minute, switch equations with someone near you. See if it checks out.